Hello and welcome to Combinations Part 1. As you can see, to illustrate, I have 5 uniquely different letters. And what I'm going to do is I'm going to try to pick 3 from these 5 letters. Well, that would be 5 pick 3. And the assumption would be that, yes, order matters. Okay, in other words, if somebody said, we're going to pick 3 letters from these 5, and we want the order of the letters to be important, then I would count the arrangement ABC as different from the arrangement ACB, different from the arrangement BAC, BCA, right? All of these they involve the letters or the cards A, B, C, but the order is different, so I'm counting them as different arrangements. Okay, now suppose somebody comes along. Okay, so here's where stop. And somebody says, I want you to pick 3, all right, but I don't really care about the order. Suddenly somebody says order maybe doesn't, let's clean that up a bit, doesn't matter. Okay, if order doesn't matter, then shouldn't I count all of these 6 groups here as 1? Because they all use A, B, C. Doesn't matter what the order is. They all have an A and a B and a C. So these should count as 1. So how do I fix all this? All right, let me clear off the screen and I will show you. Okay, so here's what we had previous when order mattered. We said we took 5 items and we picked 3. And this is all of the possible groupings where order matters, but the problem is if you look at each little group and you say, hey, these have the same 3 letters, I don't want to count those as different arrangements. So what I'm going to do is I'm going to divide this by how many ways there are to rearrange those 3 letters. Like if we look back at the ABC, how many different ways are there to flip around and rearrange ABC? Well, those are 3 things. There would be 3 factorial ways of rearranging them. So what I'm doing is I'm dividing by that number, and that's going to take out all of this, counting these as separate arrangements. Now, if I were to do the math on this, here's what the formula looks like for permutations. It's 5 factorial divided by 5 minus 3 factorial. And then I'm dividing it by 3 factorial. So you know what? I'm going to creep that underneath. Okay, instead of writing divided by 3 factorial, I can just throw it on the bottom of this fraction. And now I can just work it out. I've got a 5 times 4 times 3 factorial on the top. On the bottom, this 5 minus 3 is a 2 factorial. And then I have a 3 factorial. Let's cancel the 3 factorials, and I end up with 20 divided by 2. So there would be 10 arrangements where the order doesn't matter. Now, this is called a combination. So here's the important thing is, when order doesn't matter, like in the example you've just seen, this is called a combination. Okay, different from a permutation. And we write it this way. We write 5, choose any 3. And the formula that you've just seen in action looked like this. We had 5 factorial on the top. Then we have a 5 minus 3 factorial, as well as a 3 factorial. Now, let me generalize that for you. What if this was n? Choose our things. Then on the top, you would have n factorial, and directly underneath there would be n minus r factorial, and then an r factorial. And the big thing you can see that's different from the permutation formula. If we had n pick r, okay, they're very, very similar formulas, okay, but the big difference is we have all the beginning ingredients the same, but in the combinations we've thrown in the rearranging of our items, okay, and that's so that we obviously will have fewer arrangements. Okay, I think that's where I'm going to stop talking about combinations for this time.